All right, so scale. We're gonna start off with section 10, 11.1, which is vectors on a plane, and we'll start off with some basic definitions. Okay, so first off, the word scalar. You might see the word scalar used in problems. It's basically just a number. Okay, so instead of using constant, like we do, right? Constant's just a number. A lot of times vectors have to deal with physics, and in physics, the word constant means something else, like constant gravity, stuff like that, gravitational constants, universal gravitational constants. So, since they don't want to mix up the word constant with things in physics that mean constants, they change it to scalar in vectors. Okay, so scalar is just a number, kind of like area or volume. Temperature, mass, and time. So you can put like temperature, mass, time, etc. Things like that. Okay. So it's just a constant number. Okay. But then we get vectors. Now, again, if you've taken physics, you know that vectors are not only are they numbers, but they have direction as well, right? So these are numbers with direction. So, force is an example of that. They usually say like pushing something with a force of 50 newtons east, west, up, down, right? They give you some kind of direction with that. Velocity, acceleration, and other things like that. Okay, so when you're driving on the freeway, the posted speed limit is a scalar. Because they don't say that your speed limit's 65 miles an hour east, 65 miles an hour north, 65 miles an hour, right? It's just 65 miles an hour. When you're traveling east, the sign does not say 65 miles an hour, but then you go west and it says negative 65 miles an hour. I mean, does that make sense? Like, think about it mathematically. Would it make sense if they had a positive 65 as you go east, but a negative 65 as you go west? It actually does. Because with direction, west is negative, right? Down would be negative, right? So if you're traveling south, all those speed limit signs could say negative 65 miles an hour, and it would make sense. It would actually tell you you're traveling south or west, right? But they don't do that because a speed limit is just a scalar, right? It's just telling you don't try not to pass this speed limit, right? We don't care which direction you're going, don't go faster than this, right? So there's that. Usually they will draw stuff like this just to kind of give us an idea of what a vector looks like. So let me draw this out. So this usually is considered the initial point. All right, so that's an initial point. And over here, they would call it the terminal point. And if this is point P and this is point Q, then this is denoted as PQ, and there's a little arrow on it, right? So that's our vector PQ. Now this is called a directed line segment. So a directed line segment. Okay, now the length of this line is called a magnitude, okay? So let me write that down right here. Magnitude. That's the length of the directed line segment. Okay, so the length of the directed line segment is called the magnitude. And usually magnitude has notation that looks like this. Let me give you that notation. It's a double bar. Okay. So the line segment PQ, well, actually the vector PQ, if you put double bars on both sides, that means you're trying to find the magnitude of it. Remember, magnitude is just distance, so you can find magnitude using a distance formula. Okay, so that's how you find magnitude, using a distance formula. Now, really quick, let's do an example. And you might say, well, I haven't even learned enough of this stuff. How am I going to do an example? Well, most of this stuff you already know how to do. We're just kind of changing the wording on it. So we're going to say, let vector V be the directed line segment from 0, 0 to 3, 2. Let vector U, by the way, right now as I'm writing this out, in books, they may either use that little arrow on top, or else they might bold the letter. So you'll see like, there might be like an X like that, and then you'll notice there's like a really heavy X like that. Okay, 1 is just a coordinate or a letter. The one on the right side, that's considered a vector. Okay, so different books will do different things. So I learned on books that used to do the arrows, and then other books that I learned, they had the bolded letters. Okay, and the way you know to look for that is because you know obviously the topic you're dealing with is vectors, so you kind of pay more attention to it. Okay, so if they don't have the little line above it, it's okay, but just know that it might be a bolded letter. So be the directed line segment from 1, 2 to 2, 4. Okay, so we got two vectors. Show that vector U and vector V are equivalent. Vector U and vector V are equivalent. So remember, a vector is considered a number with direction, right? So what I got to do is prove that both of these vectors are going the same direction. And I got to prove that both of these vectors have the same magnitude. Okay? To prove magnitude, I can use distance formula. So let's do that. Let's show magnitude first. So the magnitude of U. Okay, so the magnitude of U. Well, we're going to do 2 minus 1 squared plus 4 minus 2 squared. Okay, so again, we're just getting the points that are given to us. All right, so it's x2 minus x1 quantity squared plus y2 minus y1 quantity squared, right, for distance. So we get square root of 1 plus, what is this, 4. So this is radical 5. Okay, now the magnitude for V. Okay, so magnitude for V is, oh, you know what? I just realized something. I'm like, wait a minute. This doesn't look right. Let's do magnitude for V. I'm going to change U because I realized it's not supposed to be 2, 4 for U. It's supposed to be 4, 4. It's 1, 2, 4, 4. I wrote 2, 4 by accident, but we'll fix that right now. Let's do magnitude for V. This is 3 minus 0 squared plus, and then 2 minus 0 squared. Well, that's 3 squared, which is 9, plus 2 squared, which is 4. So that's radical 13. So at this point, I would have noticed, wait a minute, if I'm supposed to show that they're equivalent, they're not equivalent. This is when I said I don't know if I messed up somewhere. The reason why, I'm going to change the color here. I'm going to make it green, okay? This 2 should be a 4. I just made it a 3. It should be a 4. Okay, so that 2, so instead of the point 1, 2 to 2, 4, it should say 1, 2 to 4, 4. Okay, which makes this become a 4. So 4 minus 1 squared, which makes this become a 9. And it makes that become a 13. So radical 13. I apologize for that. I could have swore I saw 2 there, but maybe I was looking above. So what you should note is after we do the distance formula for both using the correct data, they both have radical 13. So their magnitudes are the same. Okay, so that's good. That shows equivalence in magnitude. Now I got to show that they're going in the same direction. To check direction between 2 points, you can always use slope. And if the slope matches, that means that they're going in the same direction, right? They're making the same angle. So let's find the slope for u. So I'm going to find slope for vector u. And then we'll find the slope for vector v. Okay? The slope for vector u is going to be 4 minus 1 over 4 minus 2. So that's 3/2. Okay? So it's y2 minus y1. I'm messing up here. I'm writing them wrong. I apologize. I don't know why my eyes are going too high. So y2 minus y1, 4 minus 2, over x2 minus x1, which is 4 minus 1. So that's 2/3. Okay? Sorry about that. And then the slope for vector v is y2 minus y1, that's 2 minus 0, over x2 minus x1, that's 3 minus 0. So that's 2/3. So you'll notice the magnitudes match, the slopes match. So all you got to basically say is both vector u and vector v have the exact same magnitude and direction, thus making them equivalent. So whenever they ask you to prove that 2 vectors are the same, you want to check magnitude, you want to check direction, and if they match up, then you got equivalence.
I'm going to get picked up.
Okay. So, any questions on this one besides me messing up on the point? So hopefully that doesn't seem like, okay, this is going to be a hard thing to do. I mean, it's not too hard to do. Like I said, for today, we're basically just going to do a lot of definitions. And that's going to be it. We do have like one more example, I think we do, but after these next definitions. All right, so let me write down the definition of component form. Okay, so definition of the component form of a vector. So it says if vector v is a vector whose initial point, so is a vector whose initial point is the origin. Now, whenever a vector has initial point at the origin, we say that it's in standard position. Okay, so we call it standard position if the initial point where you start the vector starts at 0, 0. Okay? So if v is a vector whose initial point is the origin and whose terminal point, so terminal point is v sub 1 comma v sub 2, then the component form is given by, and they write it like this: v sub 1, not v sub 1, vector v is equal to v sub 1 comma v sub 2. Notice it's not using parentheses like we're used to. Okay, it's using like the less than, greater than symbol. That's how another way you can tell something is a vector, based on that notation. V sub 1 and v sub 2 are components of vector v. So we're going to put right here, note v sub 1 and v sub 2 are components of vector v. Okay, if the terminal point is the initial point, so let me keep writing this down right here. If the terminal point is the initial point, then we call it the zero vector. So the zero vector. And usually they'll write it like this, which has component 0, 0. Okay, so we have vectors that are written in component form, right? V sub 1 comma v sub 2. And the v1 and v2 are considered components. If the terminal point is the same as the initial, we call it the zero vector. The reason being that the line segment has no magnitude, right? It's the same, it's just a point. So there's no magnitude to it, so we call it the zero vector. And it doesn't even have direction, okay? Because you can't do 0 over 0 in a sense, right? So if they say that 2 points or 2 vectors are equivalent, so let me kind of just put that right here, to say that vector u was equivalent to vector v, so that we just did that, right? Then we know that vector u, so notice how I'm writing this in component form, and vector v are equal to each other, and that u sub 1 must be equal to v sub 1, and u sub 2 must be equal to v sub 2. Because if 2 vectors are equal to each other, then their components must equal to each other, because they have to have the same magnitude, they must have the same direction. So if you ever see that, they say this vector is equal to this vector, then you can assume that their components are the same. Again, just a lot of definitions right now. Right now we're going to do one more definition, we'll do an example, then talk one more definition, then we're done. Okay, and then tomorrow we'll talk about resultant vectors and get into length of scalar multiples, standard unit vectors. That'll probably be day 2. And then probably next Tuesday, we'll start doing some of the word problems. Okay? So I'm not trying to rush through any of this stuff. But the first day is always the worst because you get a lot of definitions. Okay? After that, we kind of do a little bit here and there. So, conversions. So sometimes they want you to convert a set of points into a vector and stuff like that. Okay? So two ways that they want you guys to know conversions. They say if point P, which we'll call it P1, P2, and point Q, which we'll call Q sub 1, Q sub 2, are the initial and terminal points respectively. So are the initial and terminal points respectively then we can call vector V the same as vector PQ. Okay? So we can call vector V the same as vector PQ. Now, if we do that, we're saying that in component form, vector V, V sub 1 comma V sub 2, is the same as cube sub, I guess you could say Q sub 1 minus P sub, oops, I put the wrong number there. Q sub 1 minus P sub 1, comma, Q sub 2 minus P sub 2. Okay, because that's the way we find the vectors. We just take the distance between them, right? So we subtract the first two x values and the second two y values. So those are my x and y values. I'm going to put right here leading to, and our magnitude. So it's going to lead to our magnitude. And this is kind of a shortcut to the magnitude, just so you know. Sometimes they'll just give you the vectors. Magnitude of vector V is just the square root of V sub 1 squared plus V sub 2 squared. Now, the reason why they tell you this, because this is essentially the distance formula. But they're saying if you're given a vector, if you know the vector is vector 2 comma 3, then to find its distance, just square the components, add them, and take a square root. So 2 squared, that's 4, 3 squared is 9, 4 plus 3 is 13, take the square root. That is your distance. You don't have to like draw it out and say, okay, one of the points is 0, 0, the other point is 2 comma 3, let me draw a line, let me find the distance by subtracting x's and y values. They're saying, look, if you know it's a vector, then just use the components in the formula. That's all. All right. So that's the point of this conversion definition. Okay. They're saying this is how you can convert your definition of a vector into your magnitude without having to spend too much time finding the points. Okay. And then the last one for conversion says if vector V is equal to V sub 1 comma V sub 2, then vector B can be represented in standard position so notice we're going to represent a vector as points as a point P, let's say 0, 0, and a point Q, we'll call it V sub 1, V sub 2. So if you want to change a vector into a set of points, you use your standard position definition. In other words, one of your points will start at your origin. The other point will just take on the components of your vector. So if you had vector 4 comma 6, then your 2 points will be 0, 0, and 4, 6. Okay? If you had vector negative 11 comma 8, then your 2 points will be 0, 0, and negative 11 comma 8. All right? It's not hard to convert these things. It's almost like, okay, duh, that's easy. Well, yeah, it's easy, but they just want to make sure you know that you can go from vector to points or from points to vectors. Okay? And in this case, from points to vectors, they gave us a definition for magnitude that might be a little easier. Okay? So real quick notes. So note, if the magnitude of vector v is equal to 1, we call it the unit vector. And we'll see a lot of this later on. So we'll call it a unit vector. If the magnitude of v is equal to 0, we call it the zero vector. I mean, makes sense, right? It's only one unit, so it's going to be a unit vector. For 0, we'll call it the zero vector. All right, so let's do a quick example. And do we have time to, maybe we'll stop there and maybe tomorrow we can continue with the rest. So a quick example and then we'll stop. So here's example number 2. Find the component form. We're going to find the component form and length, I guess you could say magnitude, of the vector v that has initial point and they're giving us 3, -2 and terminal point of -2, 5. Okay, so what we're going to want to do is we're going to want to convert this stuff, okay, into vector form. Do you have to? I guess you don't have to, but it kind of is a little helpful. So we know that vector v is going to be composed of 2 different points, right? So vector v is basically going to take q sub 1 minus p sub 1 and q sub 2 minus p sub 2. And then once we figure out those subtractions, we can write it as a vector. So the vector is q1 minus p1. So -2 minus 3, right? This is my q1 here. I'm sorry. Where is it at? Q. Yeah, so we're going to do the x components first. So -2 minus 3. So this right here and this right here. So that's going to be -5. Okay. Q2 minus P2. The sub numbers tell you the x's and y's, right? The 1's are the x's, the 2's are the y's. So we take the y's. 5 minus -2. That's 7. So vector v is -5, 7. Okay. Now, so we found its component form. Now they want the length, so they want the magnitude of v. Okay, so we did find the component form, so there it is. Now they want magnitude of v, so that's just going to be square root of -5 squared plus 7 squared. Right? Just take the components and square them. So square root of 25 plus 49. So yeah, we're going to have 74. If you divide that by 2, you're not going to get anything helpful. So there's your magnitude. Your magnitude is radical 74. So that's all the problem wanted you to do. Just find the magnitude for it and find the component form for it. All right. So I know most of this stuff does not seem like it's going to be really hard to do, which it isn't. We will eventually get to some word problems which get a little bit more tricky. But for now, this is all we're going to show you. Okay.